my will increase mx. Okay? So if you think of that, you'll see that the only possible way the solution can come out is oscillation. Okay? So suppose after some time my is positive. Okay? If my is positive, what happens in the system? If my is positive, then dmx dt is positive. Correct? Now, if dmxy this is positive, then suppose you are here. You are at this point where mx is 0. And my is positive, that will increase mx to some positive value. Okay? So what I'm trying to suggest, if you just look at the equation, even without solving, you know that this solution has to be oscillatory. Okay? But this approach of doing the differential works because you did not have any mx in your first equation and no my in the second equation. Suppose I give you, instead of those two equations, suppose I give you dmx dt equals k1 mx plus k2 y and dmy dt equals k1 prime mx plus k2 prime my. Will you be able to solve this using the technique I just discussed, like differentiating ones? No? So in this case, suppose I differentiate one more time, I get d2 mx dt2 equals k1 dmx dt plus k2 dmy dt. Correct? So that means I can replace now dmx dt through this equation and dmy dt from this. Dmx dt and dmy dt I can replace by these two expressions. But if I do that, I'm going to get a mix of mx and my. So I didn't decouple the equations. Correct? So in the previous case, these two equations got separated. So I have to d2mx dt2, omega 0 square mx, d2 my dt2, negative omega 0 square my. So you could solve them separately. There is no coupling. Now mx is a separate equation, my is a separate equation. And here, that's not the case. So you need to go back to the scheme which I discussed first, which is using m equals u to the power lambda t, calculating the eigenvalues, writing the solution as sum of two modes. But now there is a choice. And that's, I believe, it's going to work for any problem. Either you calculate the eigenvectors and do through the eigenvector approach, or you write the solution in through, this is B1, through cosine plus sine, and then calculate these unknown constants. Okay. So I plan to discuss a little bit of Laplace transform method of solving ODEs. Can you raise your hand if you have seen that before? In this side? No talking, please. So, okay, some of you have seen that. So I can discuss it. And all of you have seen Laplace transform? Like the regular Laplace transform? Yes? Okay. So let's postpone that for the later part of the lecture. And let me start discussing the numerical solution, which is very, very important. Now, what MATLAB does, it uses numerical solution theories, okay? So what you are going to see here, like the theory of numerical solution, MATLAB has inbuilt program that exploits those numerical solution theories, okay? And let me start with a simple example where you are kind of forced to do numerical solution, and which is very widely applicable. So imagine receptor ligand binding when two cells are in contact. Cell. So definitely this is a very, very common biological process. It happens all the times. Like whenever a cell is interacting with a second cell, these two cells exchange information through this receptor ligand binding. So each cell has a set of receptors on its cell surface. Probably you're all familiar with that, which I might call R, and then the ligand on the other cell surface. Okay? So for example, if this is an immune cell, the other cell is going to be an antigen-presenting cell. So this immune cell is going to recognize a foreign virus protein on the other cell as the ligand, and then it can get activated and trigger immune response. Okay, that's one example. And so that's more basic biology, but can you tell me of biomedical applications of this process? Which is used as actually a lot these days. Of receptor ligand binding.
Assays? Assays?
Can you describe it a little bit more?
Like an ELISA assay? So you like test for...
Yes, that's very similar. That's like ELISA assays, where you bind antigen with antibodies and make detection. And also a lot of medicines today are nothing but blocker of these cell surface receptors. So you suppose you have a tumor cell which grows through signaling through this growth receptor on this cell, and you create an inhibitor of this signaling. So what you do, you basically create another ligand. This ligand, suppose, can bind with these receptors quickly or stronger than the other ligand. Then what will happen? This cell will not get a chance to activate this growth signaling pathway. Okay? So if you can create such ligands, they will bind to this growth receptor and block the signaling. And that's how you can save like tumor cell from growing. Okay? So there's a wide range of applications of receptor ligand binding in today's drug discovery. So it's a huge application. Now, if you want to describe such a process, receptor ligand binding, suppose you have receptor molecule R and binding with L, and they create complex C. And you want to measure how fast they bind with each other. And there are rate constants. So do you know those rate constants from chemistry or biology course? Like how do you, affinity, are you familiar with the affinity constant? Yes? K on and K off? Yes? So this reaction can happen with a forward rate constant K on and backward rate k on and the backward rate constant k off. So if I want to write the rate equations for this, how fast they change, because this is important. So if you want to create another ligand which can bind in a competitive manner with this receptor, you need to do dr dt k on RL plus k of C. Then dl dt equals negative k on RL plus k of C. And then the complex I can write dc dt equals k on RL minus k of C. Okay. So can you tell me like why I chose this positive and these two terms negative? Yes?
Because in this way, that drdt k on represents the movement from R and L into becoming compound C.
Correct. So if you take one molecule of R and one molecule of L and create another molecule of C, then you are losing R and L. Okay? So when you are creating the complex, you are losing free R and free L. So you have two negative here, and you are creating the complex, so you have a positive term there. And in a similar manner, when you go back, when you are breaking C into free R and free L, then you are losing your complex. So you have a negative sign here, but you are gaining free receptor and free ligand. So you have two positive terms. Do you follow? All of you at the back? Yes? Now, if I give you this equation, which I started discussion of ODEs with this, Kn Nt equals N0 e to the power kt, right? That's very simple to solve. If it's, so suppose instead of n, I write for the complex, or no, let's keep it that way. But once I have receptor ligand binding, this equation is no longer a linear equation like this. And the reason is I have R times L as a product. Okay? So can you think of ways of solving this equation? I mean, solution means this kind of analytical, this or this type of analytical solution. Yes, no? So you might think that there might be suitable transformation or exponential lambda t type trial solution that might work here, but it does not. So because this is a nonlinear equation, no analytical solution. Okay. So you see, this is not very complicated. It's simple receptor ligand binding. I have a term like RL minus C. But even then, this equation is not solvable. It's solvable only for the steady state. Okay? So only when you are considering steady state means when dc dt equals dr dt equals dl dt equals 0, then you can calculate exactly. So what's going to happen, your R initially has some value, say R0,